Hi, this is Kiffer with this week's lecture on sample size and power calculations. In this lecture, as the title kind of suggests, we're going to discuss two related concepts that are fundamental to epidemiological research, being sample size and power calculations. On slide 2, we introduce the fundamental questions related to sample size and power calculations. Namely, we are examining how large of a sample size we need to detect a difference of a given size. These questions come into play at multiple points throughout a research study, such as when you're writing a grant or planning how many samples to recruit, or when you're reporting the confidence in your results of an analysis you've already completed. On slide 3, you can see that one of the primary considerations when determining sample size is to balance cost and power. The more participants you recruit and the longer you follow them for, the more your study is going to cost, which is kind of obvious. And the greater the power you can detect, which you can use to detect smaller and smaller differences between groups or to generate more accurate point estimates. On slide 4, you can see that in the real world, you often have methodological restraints. You're not able to follow people indefinitely, and you can't follow an infinite number of participants. This ultimately limits your power. Now on slide 5, when we consider what it means to limit power, we should recall the two basic types of error that can occur when conducting a hypothesis test. In cell A, we represent the possibility of rejecting the null hypothesis when the null hypothesis is in fact true. This, as you know, is called a type 1 error. A type 1 error is usually represented by a confidence interval, or p-value, which you should be familiar with. With a p-value, you're basically saying this is the probability of making a type 1 error, and with a confidence interval, you're saying, is the probability of making a type 1 error included in our range of estimates? Now in cell B, you represent the possibility of correctly rejecting a false null hypothesis. And in cell C, we represent the possibility of, again, correctly accepting a true null hypothesis. These are represented by the expression 1 minus beta and 1 minus alpha, respectively. Because remember, alpha is the probability of making a type 1 error. And beta, as you can see in cell D, is the probability of making a type 2 error. Now, what is a type 2 error? Well, a type 2 error, as you can see on this slide, is the probability of accepting the null hypothesis when in fact it is actually false. This is represented by beta. So when we're talking about power, represented by the expression 1 minus beta, we're really talking about the ability of our study to make the correct decision of rejecting the null hypothesis when the null hypothesis is false. So on slide 6, this can be depicted graphically. Imagine that these are two probability distributions. The blue one represents the possibility that the null hypothesis is true, and the red one represents the probability that the alternative hypothesis is true. So this could be two samples. You hypothesize that there's a difference between two groups of people. You could hypothesize that there's a difference before, pre and post intervention. You could hypothesize that there's a difference just from any random null value, or maybe a previously observed null value, and what you expect to observe in a new sample. Therefore, the area with the red lines to the left of your significance level, often 0.05 as it happens to be, is the probability of failing to reject a null hypothesis that should have been rejected. So if you obtain a value in that region, if your sample mean or whatever it is that you happen to be sampling at the moment, if you obtain an area in that regions, you would make a type 2 error, represented by beta. Similarly, if you obtain a result in the blue-lined area, you might reject the null hypothesis when in fact there is a good chance that the null hypothesis is true, putting you at risk for a type 1 error, represented by alpha, your type 1 error rate. However, if you obtained a value in the blue area without the lines, represented by 1 minus alpha, you would fail to reject a true null hypothesis. You would fail to reject a true null hypothesis, which is the outcome you want. And likewise, if you obtained a value in the red area, represented by 1 minus beta, you would correctly reject the false null hypothesis. Again, that's the result you want. And so the unlined areas or the unshaded areas, that's where you want your mean to fall so that you can make a correct decision about whether to reject or fail to reject the null hypothesis. Power is therefore represented by the region in red, just the whole region, minus beta, which as you can see is the red lined area. Mathematically, this is just 1 minus beta. It's the unshaded area. And so hopefully that gives you a little bit better sense of what it is we're talking about. Now let's move into, starting on slide 7, examining some of the factors that influence your power of your study. So on slide 7, you notice that the difference of the two probability distributions increased. I basically spread them apart. Perhaps this is because you revised your hypothesis regarding how different the observed value would be from the already existing value, the null hypothesis. You can see that this reduces the probability of error because the volume of the unlined areas increases. And remember, these are the regions in which you are making correct decisions regarding your hypothesis test. This means that if you are okay with measuring larger, less precise differences, then you are less likely to make a type 1 or type 2 error. Whereas if you want to measure smaller differences, the overlap between the two distributions would increase, and you would increase the probability of error. While ideally we would be able to detect even the smallest of differences, generally speaking, this isn't always possible. As such, when we measure small differences, we accept that there is some chance of error. That is why we generally reject null hypotheses at, say, 0.05, because we accept that about 5% of the time, we might incorrectly reject a true null hypothesis. While there's nothing special about the alpha level 0.05, it is widely accepted. And similarly, a power of 80%, or in other words, a type 2 error rate of 0.2, or 20% of the time you're going to make an error, indicates that we are usually willing to accept the chance that we are failing to reject a null hypothesis when in fact it should have been rejected. There may of course be times when you want to be more certain that you are making a correct acceptance of the null hypothesis, and you would want to increase your power perhaps to 90% or 99%, as you would a p-value as well. Ultimately, is what that says is you are tolerating less probability of falling in that beta area. Now, in addition to impacting power by accepting larger differences between two values, slide 8 shows that we can also increase our power by increasing our sample size. This is because when you sample more and more people, you increase the precision of your estimates, and thus you narrow the probability distributions of your potential estimates. This is the law of large numbers. This is the normal distribution. This is the theory that makes it kind of all work, is that you shrink them, and as you increase your sample size, you shrink this range in which you are likely to draw a sample that lands closer and closer to the true mean value. And so you can accomplish this by increasing both the number of participants, but also the duration of the study, following each participant for longer periods of time. And so that gives you, remember, person years, which we've talked about. Now, this is really kind of fundamental to understanding that as your sample size increases, you get closer and closer to a true value, and that's just basic statistical theory. So finally, on slide 9, another strategy to decrease your type 2 error rate is to reduce your alpha. As a result, you shift you shift and reduce the area in which you fail to reject the null hypothesis represented by beta. However, as you can see, this increases your risk of a type 1 error represented by alpha, which is the probability of rejecting a true null hypothesis. Because of this basic problem that happens when you sacrifice some of your confidence for the sake of trying to increase your power, the preferred strategy to increase power is to just increase the number of participants like we showed on the last slide. This saves your study scientific integrity and reduces the probability of a type 1 error, which is often more troublesome and less preferred by researchers. Now, As shown on slide 10, there are also factors outside your control that might potentially impact your power. Here we've increased the spread of the potential values in your true and null hypotheses. In a data set, the standard deviation, you should be familiar with, measures the spread of individual observations and is estimated using sigma. Oftentimes, this is even estimated by your sample standard deviation, which is obtained through a pilot study, or based on previous research on the variance and spread of data. Now, as the standard deviation increases, so in other words, as your spread increases, as the probability of drawing any random number gets wider and wider to approximate the true mean, it becomes harder to detect differences. This is similar to how trying to measure more and more precise differences is difficult, because ultimately there is greater overlap between the null and alternative hypotheses. Sometimes this is referred to as noise, right? Because that spread, that noise in the data makes it hard to detect differences accurately. And so, in review, on slide 11, we can see that there are a number of factors that impact power of any given study. First is if you hypothesize a larger difference between the null and alternative distributions, this difference is easier to detect, and thus you have more power to make correct decisions. Now, if you increase the number of people or the length of time you follow them, your power increases because you have a larger sample size that's narrowing that range, kind of squishing it in and focusing in on the true mean of the data. And then if you decrease the level of significance, so you're moving from say 0.05 to 0.01 for your significance level, you increase your power by shrinking that region at which you reject a null hypothesis, right? And you're increasing the region at which you would fail to reject. And finally, there's the spread or variability of the data, which you don't have a lot of power over, but as your data spreads out or variability increases or your variance grows, it becomes harder to detect differences, and thus your power decreases. On slide 12, you can see that the relationship between these variables can be illustrated using what we call a power curve plot. These can be generated by calculating the power across a range of potential effect sizes for various size samples. And as you can see here, a sample with a larger number of participants, the red line in particular, achieves higher power at a lower level of detection. And why? It's because it has a higher sample size. And so with a higher sample size, your power curve is much steeper, so you have more power more quickly in detecting smaller differences. But if the difference you're trying to detect is just really big, maybe you only need 25 participants because, yeah, that could potentially still reach, full power. Or maybe you're willing to accept less than 100% power. Maybe like normally we're willing to accept 80% power. And in that case, you could choose a line that, matches the level of difference that you're willing to detect. And so these power plots, as they're called, can be created in statistical software based on what we call power calculations or sample size calculations, where basically you plug in a whole bunch of different values, changing all those factors we've discussed here too, until you kind of get a sense of, well, at what points does it change kind of the feasibility of our study based on what we're doing. And so on slide 13, we can see the first of such formulas that might be used to create a power plot. Though rather than calculating power, here we're calculating sample size. This tells us the number of participants that we need to recruit into each group for a given power, variance, desired difference, and confidence level. So you plug those factors in there. They're color-coded in there, and the examples that will follow in the previous slides will follow this kind of color coding. But you can see that is what's basically being included is that Z alpha divided by 2 is your critical value of your confidence level. And remember, it's a two-sided test, so that's why there's the divided by 2. There's the Z beta, which is the critical value under the normal distribution of beta. And so those are generally pulled from tables. There's also just kind of these standard ones that we use. If you stick with 80, an 80% power, then your critical value is 0.84. If you stick with 95% confidence, then your critical value is 1.96. Then you have the sigma squared, which again is the variance of the population. Here it's often just by sigma, which is an estimate of your standard deviation, often approximated by S, which is just the population or the sample standard deviation. And then divide that by the difference you would like to detect. And so that's D there. And so the size of the difference you wanted to detect. So you just plug those values into the formula. An example of this is on slide 14, in which we want to create a study to detect a 3 milligram difference in serum cholesterol between men and women. You see men got 180 milligrams per 100 milliliters, and women had 177 milligrams per 100 milliliters. And this was in a pilot study, and you want to see, well, in a bigger study, in a larger study, we want to see if this is true. Now, we were fortunate enough, because we conducted a pilot study, we saw, oh, there's a 7 milligram variance or standard deviation in that sample size. So that's not the variance, that's the standard deviation. And that standard deviation tells us, well, that's what you need to worry about in terms of spread. And so then you want to determine if that is true in regards to the size of the difference. You're going to approximate your variance by using that pilot study standard deviation. And you want to keep the traditional, conventional 80% power, 95% confidence. And you can toy around with these calculations to see how those affect, and maybe create a power plot of your own if you want to kind of get a better working sense of how these work. But on slide 15, you can see that the formula is basically plug and go. We take the z-scores. These are, again, from tables of 1.96 for the confidence level, of 0.84 for the power. We plug in the standard deviation, which was 7. And so 7 squared is the variance. Remember, that's replacing sigma, and sigma squared is the variance. And then we're detecting a difference of 3, so we plug in the 3 there. And then we basically solve just algebraically. You could even rework this equation algebraically. Say you want to solve for the z-score so that you can convert a z-score back into a power level. You could then treat it as a power calculation. But here, like I said, we're just looking at sample size, and as what that ultimately gives us is 86 people per group would be needed to detect that 3 milligram difference between men and women. Now, remember, you're probably going to want to round that up, so we always round power calculations up to 86, because in order to achieve that power, you need at least 85.29, and because there's no people that are just 0.29 people, those ultimately get rounded up into a whole person. And so it's also important to add additional persons to account for dropout, and so that's really the number of people you need to have completed your study to get a good estimate and to accurately complete your study. And so if you expect that there's certain level of non-response or a certain level of dropout in your study, you're going to actually want to recruit more, and so you may want to estimate or look in the literature about what dropout rates are and then overestimate for a sample. This is particularly important when writing a grant, because you need to show them that you've thought through this kind of process of worrying about these people who are going to get lost. And because if you have a 20% dropout, right, that's going to take your 86 down 20%, and then you're not going to have the power you thought you would. And so on slide 16, I provide you with a formula for the recommended number of individuals required to detect a difference between two proportions. And so this formula is a little bit different because, remember, we're considering proportions. And so by changing the inputs here, the confidence level there in blue, the power there in red, the difference of the two populations, P1 and P2, those are all you need. Now you can see how each input is related to sample size by plugging these factors in at various kind of levels. And remember that this can be solved algebraically to solve for power, which gives you the critical z-score, and then you can use the z-score and reverse it, look it up in a table. However, as with the last example, we're going to work in the other direction, calculating sample sizes. I think it's best practice to calculate this ahead of time before your study is conducted, but you might very well do it the other way. And so on slide 17, I provide an example of the sample size calculations for the differences of proportion. Here, we conducted a pilot study. We observed that 5% of men and 3% of women had a heart attack. And you want to determine whether this difference was real in a bigger study. And so following convention, again, 80% power, 95% confidence. You'll notice we don't have a variance term here or a standard deviation because we're talking about proportions. And so proportions, right, are a little bit different in that one of the big problems here, instead of variance, is what comes into play is the size of those values. And so you can imagine that it's hard to detect an event that only occurs in 3% or 5% of a population versus an event that occurs in 95%, right? Because you're going to observe a lot more events occurring, and so that's going to have a bigger influence on your power for proportions. Whereas in our earlier example, when we're talking about means and estimating the true means, that's where variance comes in, because that's going to fall into a kind of a normal distribution as you sample those means. And so on slide 18, you can see that this is basically the same as the last, just plug and go. It's dependent on the confidence level there in blue, the power level there in red, the proportions of interest. In this case, we're converting 5% to its decimal representation, which is 0.05, and 3% to its decimal representation, which is 0.03. We're plugging all those values in, and we get this big value, 1,500 people, is a required sample size. Now that's quite large, and so this is not even accounting for the fact that you have a dropout rate and roundup rate. And why is that? Why is that so large? Well, it's because these values are so small, 5% of men, 3% of women. You need a big study to capture 5% and 3%. Whereas if you had a population where something's occurring at a much higher prevalence, then that's going to affect that much differently. And so with that said, on slide 19, you can see that there are a variety of other tests than those discussed here. These can all come into play as you engage in more complex statistical analyses, such as when your samples are dependent, or when you're comparing within individuals, or when your outcome variables are more complex than proportions or means, or when you're using non-parametric tests. But as you might expect, it's easier just to use statistical software packages such as R to do these various calculations. If you're interested in using these, this is done in the power package in R. For each of these functions, you'll need to know the effect size, the desired significance level, and the desired power to calculate the sample. In doing so, you should note that the effect size takes into account the difference between the variance and your standard deviation. And so you can click that link down below, and that'll kind of give you a more in-depth kind of description of how to calculate that and how to create a simple power analyses or any of these more complex power analyses using R rather than doing it by hand. Likewise, on slide 20, there are similar procedures in SAS, which you're free to explore as well if you have access to SAS. And that's just how real-life power calculations are done. We're not often doing it by hand. We're just plugging our values into formulas in statistical software. And so that's using the proc power procedure in SAS and the power package in R. And with that, I'll leave you to review slides 21 and 22, where you'll be able to get some guidance and get a sense of what's going to be on the quiz. Now, as you do these, as you practice these, I want you to make sure that you have a strong working knowledge of each of these concepts. Don't just be able to answer them based on kind of rote presentations, but actually understand if a type 1-2 error occurs when the null hypothesis is not rejected but is false. Understand why that is, especially with respect to kind of the probability distributions that we were showing earlier. And if you do that, if you have a good understanding, then you should be pretty good. But again, if you have any questions, I look forward to seeing you on the discussion boards this week. And hopefully you'll be able to answer each other's questions, but if not, then I'll go ahead and step in. Okay, with that, have a nice week. Okay, bye.